So the last approach we're going to talk about for achieving privacy is called differential privacy, and it solves a problem that we have with k-anonymity, which is probably easiest to illustrate using the example that I had on that table we were just ending the last segment with. So if you look at the men in this chart with fewer than 100 friends, you recognize, oh, here's one, fewer than 100 friends in male, here's another one, fewer than 100 friends in male, here's another one. There are actually no women in this list that have fewer than 100 friends and are male. So if you decided that you were going to have a three anonymous query for the friend attribute of less than 100, you would still learn something about all of those people. That if you know for sure they have less than 100 friends, then you also know for sure they are male. And this is called the L diversity problem, and there are techniques to try and address this by increasing the diversity inside of those K anonymous result sets. And there are problems with L diversity that can be resolved with M invariance, and problems with that can be resolved with T closeness, and a wide variety of other techniques for addressing this general issue with K anonymity. Well, differential privacy is intended to address those kinds of issues, right? So large aggregate data sets can be privacy protective, but these differential results or off by one type results are very, very difficult to protect using traditional techniques like k-anonymity. So if you happen to be the only male over 30 who dislikes football, you're going to stick out, even in a k-anonymous data set. If you happen to be adding one employee and then publishing the mean salary before and after, then you're basically publishing that one employee's salary, right? It's very easy to calculate if you have the total number of people and the mean before and after. Those differentials are very, very difficult to protect. So differential privacy is a technique for revealing aggregate properties of this data set while still protecting those individual properties in the data set. And I'm going to go through like a really high-level overview of how this works, but first I want to show you some things that it cannot promise, right? It doesn't protect against probabilistic inferences. So if you just happen to know 70% of men suffer from male pattern baldness, and I don't actually know if this is the statistic or not, it kind of doesn't matter. If it's just an assumed fact of the world, then any attacker can kind of learn that you have a 70% chance of suffering from male pattern baldness using the data set, right? If you're in a data set and they know that you're male, you can learn this piece of information. Now that's not a particularly strong guarantee, but I have actually seen people complaining about differential privacy results because you can connect it to general knowledge about the world. That's not what differential privacy is trying to protect you against. It's trying to protect you against connections with other more specific databases or datasets that would allow you to identify individuals. So this probabilistic inference, not something differential privacy protects against. And it doesn't give you perfect deniability. So if somebody knows that you're a student at UMBC, you're not going to be able to deny that you're a student at UMBC just because, or that you're possibly one of the results in a data set of querying UMBC students. Perfect deniability is just not something that's possible with differential privacy. Some of the details are going to be more important than others, but everyone's going to be in a tax data set or a healthcare data set. You're going to end up in hospital records at some point. Hopefully not very often, but you will. And you're not going to have perfect deniability for that sort of thing. Okay, so how does differential privacy work? There are basically three very simple steps. Step one, you want to add some kind of probabilistic noise to your completely accurate data set. Right? This noise is going to basically be the amount of plausible deniability that is available to everybody who is in the data set. Step two, you're going to generate a release data set. Right? We're trying to generate these anonymized releasable data sets based on the noise that's added. And then in step three, we want to make sure the underlying purely accurate, completely accurate data set has changed enough so that the next time you do step one and step two, you don't have those differentials, right? You don't reveal any information through differentials, okay? So I'm going to show you a very simple visualization of this, and we'll walk through each of those three steps in this visualization, right? So imagine we have a data set of employee salary at UMBC. And of course, here at UMBC, all of the employees make salary recorded best in millions. So 1 million, 2 million, 3 million, and probably President Hrabowski is somewhere over here, right, in the 10 million range. And then an employee number, right? Every employee is assigned a unique number. I'm just showing the first 10 employees in this particular data set. Step one is to add some kind of noise, right? And that is signified by this red Laplacian curve that I have shown here. Now I'm only showing it for this one data point for employee number 5, but you would actually want to add some noise to each of the points in the data set. So you can imagine a Laplacian curve that goes over each of these data points. And that would actually be something that you could individually tweak to make it more likely that you would end up not having these overlapping tails, right? So for example, instead of having a Laplacian that ends, you'd make sure that it could expand all the way to the end of the range for each of these data sets, or each of these data points. Now, the step 2 is to generate this releasable data set. And so when you're generating a releasable data set, you would say, okay, instead of saying employee number 5 has a $4 million salary, we're going to take this curve, this noise curve, and just draw randomly from one point in this area underneath this curve. Now, most of the time, we're going to get somewhere close to 4 because most of the area in this curve is somewhere close to point number 4. But every once in a while, we're going to get something really low, and every once in a while, we're going to get something really high. And it gives this employee number 5, plausible deniability because they could actually claim they're anywhere in the data set. You've got this curve that covers the entire range of outcomes. And most of the time, they're going to be close to 4, but sometimes they're not, right? So they have that plausible deniability. Now, step 3 in terms of maintenance is after we've generated a data point for every individual accurate data point in the data set, we want to maintain this record in the future. And so we have to make sure that we've got enough churn underlying the total employees and even churn in the salary before we do that release. One way that you can do this is sort of artificial, right? So instead of looking at literally every employee in the UMBC database, we could just take the first 80%, right? Or randomly select 8 out of 10 for every 10 employees. And then the next time that we're generating a releasable data set, we would choose a different 80% or a different random selection method so that we would not have the entire data set represented as long as we still have good statistical values for doing calculations over time. Okay, now this is a very powerful technique for protecting privacy in statistical databases, and it's the kind of thing that is actually currently being used by Apple and by the US government for the 2020 census. And I think it's a kind of technique that's worth learning more about. There's good textbooks and other information that I can make available on Blackboard if you're interested. Just contact me and we can have a conversation about this sort of thing. Again, differential privacy, k-anonymity, the notion of privacy in statistical databases is not really covered in the chapter in the textbook on data storage, but this is research that we're doing currently at UMBC to protect privacy. And I wanted to at least give you a sense of what that sort of thing looks like so that you'd be aware of something that maybe you wouldn't have had you not gone to UMBC or to a research university.